Hello. In last video, we started with a mission called understanding the gradient descent algorithm and also the backpropagation algorithm, correct? And while doing that, we basically started with a very simple problem called the handwritten digit recognition problem. And also we basically designed a very simple neural network which will do the job for us. And while doing that, we discussed or we basically defined a function, a weird function called this guy over here, the cost function over here. It's also called a quadratic cost function because it's a quadratic equation here. And I said, like, we will try to deep dive into this function as well and try to understand what's going on over here. Now before we jump into that, now there could be two questions should arise, like why you are using a cost function instead of we can just maximize the number of correctly classified images over here, right? This could be one question, and it's a very valid question as well. And second question could be, like, let's say if we are using a cost function, can we use any other cost function instead of this particular quadratic cost function? Okay, we will revisit these two questions later in this video, but let's first try to understand the current cost function we have started with. Maybe it will make sense when we end that one regarding these two questions. Okay, so to understand why we have defined that particular cost function, the idea lies in the concept of mean square error. Now this particular video will be part of this deep learning ML3 playlist. And if you remember, if you are following the video I have created in my machine learning playlist, the ML1 playlist, there in one of the video we have discussed about the detailed discussion on the simple linear regression, the least square algorithm. So this particular equation what we are currently talking about, the cost function equation, is actually the concept lies in this mean square error we discussed in that particular machine learning video. Now over there, if you have followed that one, so what we did, we basically took a very simplistic data set called the GRE score, and what we did is we basically created a chart called, based on the GRE score, what will be my chances of admission here. Okay, so I have just taken 4 points over here based on the GRE score. Like my chances of admission over here will be 50%, 99%, 70%, 84%, something like this one. Now maybe it is not reflecting the realistic part. Maybe if GRE score is high, maybe 99 should have been over here, but at least we got an idea, like the data set over here. Now if you remember, like what we did over there, let's say we want to fit a line through this particular data, just to draw a prediction line over here, because we talked about linear regression that time. So what we did, we started with a very simplistic line somewhere, let's say from along the x-axis here, correct? And then we were just moving this line something like this one. So while doing that, what we are basically doing it is something like this one. So from each and every point, this is the actual data, we are basically taking some difference, the difference between the actual data and the predicted data. Something like, let's say I will just give the seminal name whatever we have used in our handwritten digit recognition problem. So there yx was our actual output, correct? And a was our current output somewhere. So we basically have to take the difference over here, and let's say this particular difference we are naming it as a lowercase epsilon over here, the actual value minus the predicted value. And if you remember, what we did that time is, for each and every point we have basically taken the difference between the actual value and the predicted value, and we have summing it up, and then we try to minimize that particular error, right? So that's why my line was from the x-axis, the error was maximum. Then the more closer the line was going to these points, the error was getting minimized. Now at the point where there will be no we cannot further minimize it, so that will be my optimal line over there, right? So now if you notice over here, for this particular point my epsilon was positive, correct? My epsilon was positive over here because my actual value was greater than my predicted value here. For this particular point it is 0 because both are same. For these two particular points my epsilon is negative over here. Now why I did this one? Because if you see, as I said, for each and every point we want to get the difference and we want to sum it up, correct? So that we will get the function which we want to minimize it over here. So you need to basically sum it up over here. Now there is a problem over here, we discussed also in that same video, where if we just want, if we are just taking this difference between the actual value and the predicted value, it may happen that for a lot of data points these two are same, like the positive value of the epsilon is same as the negative value of the epsilon as well. So this will cut it out, correct? And it may happen that for a particular data set the value of the epsilon is automatically becomes 0, correct? But ideally there are differences between the actual value and the predicted value over there, correct? So to overcome that, what we did in that particular video is we have taken a square over there, right? So to make both of this positive value and the negative value a positive one, then we were just taking the sum. And if you see, like this particular right hand portion of this particular equation is much similar with the equation with the cost function we have defined for our handwritten digit recognition problem. Only thing is that in this particular problem both of these yx value and the a value are a scalar value, correct? But in our handwritten digit problem both are vectors. That's the difference we have, and both are like 10-dimensional vector there, correct? According to our design we did in our previous video. So we are able to establish a similar equation, but we found it out like instead of scalar these things are vector. So at least we need to know how to take difference of the vector. Okay, now not only we need to know the difference of the vector, over here we are able to get this particular difference just because like we can, both are scalar, we can just take difference and we can get the value of this particular line, the length of this particular line. So we need to do the similar stuff for the vector as well. So basically we need to have the distance between these two vectors, some way we need to calculate it. So for that we need to understand vector geometrically. So let us do that one. It is very easy actually. So if we just talk about a vector, let's say we have a vector called x. So mathematically when you write a vector, you generally write an arrow, something like this one, and this particular letter will be in the bold letter, and then you will be basically giving some numbers, bunch of numbers over here. And if you remember in the vector video for the deep learning playlist, so I have defined vector and we reasoned through it like how to represent information in vector form, right? So we basically write a bunch of numbers, and if you see, generally we talked about like generally when we talk about vector we will be seeing it as a column vector as only. Okay, now if you write in the row format, so you can always take a transpose of it and then it will become the same format over here. So just to be in the same, so just to maintain the same format, I have written the vector as like this one. Now when we talk about vector geometrically, we can represent it something like a line segment, that too a directed line segment. That means it has two properties, two important properties. One is the magnitude or length, another is the direction, which direction it points to. So that's why if you see, these vectors are extensively used in physics to denote the force in any kind of real object which have a particular magnitude and which have a particular direction as well, correct? And the starting portion from where this particular line segment starting is called the tail of the vector, and till the point where it is basically ending over there it's called the head of the vector over here. Now we may ask this question, like where this particular 3 and 2, this information fits over here. Now this is interesting. So if we start from the tail, as I said, this is the starting portion of the vector, and go this direction, let's say we make it as positive direction, or if we just talk about in terms of Cartesian coordinates, let's say we go to the x direction. So if we go to right side, let's say if this particular point is 0, if we go to this side, that means right side of the 0, that means we are going to the positive direction over here, right? So if we go this direction in 3 steps, and if we go this direction, that means in our positive y direction 2 steps, we can go from tail to head over here, right? And if you see, it basically forms a very nice right angle triangle over here as well, which we'll revisit again. So this is the overall representation of a vector geometrically. Now if we see in our Cartesian coordinate, I just draw the same vector in 3 places, and it is very easy to understand over here. If you see, like in the first place where I have started with 0, 0, that means from our origin, then I went right side 3 steps, and in the positive y direction 2 steps. So that is my vector over here, correct? Now the same vector I can draw from starting point, let's say -3. I will go at the right direction. As I said, right direction will be the positive direction. We'll talk about the negative direction as well. Right direction 3 steps, and then positive y direction 2 steps. I will reach this portion over here, this point over here. If you see, for both of these vectors, the origin and the end point are different, but both of them represent the same vector. Both have the same magnitude, both have the same direction as well. So this is an interesting factor. Like when we basically analyze the vector, so we do not need to worry about, like in the Cartesian coordinate, where it is placed. We can place this vector any point over here, but we need to make sure the magnitude and the direction of it should remain same. So if any of it is changing, let's see, if I just pull this one to make it bigger, its magnitude is getting changed, correct? So in that case, it will be becoming a different vector over there. Or if I just say rotate it somewhere in the anti-clockwise direction, so it will become another vector as well. It will not be the same vector anyway. Okay, the similar vector, the same vector I can draw to start with point -4, going this way 3 steps, this way 2 steps over here. Okay, so as I said, like in Cartesian coordinate, we do not need to worry about this one. So whenever we'll be working on the vector addition or subtraction, we will try to avoid this Cartesian coordinate as much as possible. Okay, so we got a very fair idea about how to represent a vector geometrically. Now that will just give us an idea about the vector. Now as we established in the previous slide, we need to find the difference, the length or distance between two vectors, correct? The longitudinal distance between the two vectors. So to understand that, first let us try to understand how to calculate the magnitude or length of a vector. As I said, we will be revisiting this particular vector and this particular right angle triangle it's forming over here. So this is my x vector over here, correct, which we defined in the last slide. And as I said, from this point we are going three steps, and here we are going 2 steps, and this is basically forming a right angle triangle here, right? So we can basically apply the Pythagoras theorem over here. So it's just nothing but the length of this particular side will be root over 3 square plus 2 square over here. So that is nothing but this particular notation. Within this double bar, we can write x. That means this basically denotes the length of the vector x or the magnitude of the vector x, and then the value will be this guy over here. Okay, so at least we are able to establish this double bar symbol over here, which we saw in our cost function equation. Now let us move on. Let's talk about how to do the vector addition, because we need to understand the vector subtraction over here to understand that, we first need to understand how to add two vectors. Okay, now if you see all throughout these discussions, we started with a very simple vector, a 2D vector, because we can visualize it in our Cartesian coordinate. Now the same principle applies to vector of any dimensions. It could be like 100 dimension, 200 dimension, the same principle applies over there. Okay, so we are just using a very simple vector because it is easier to understand over here. So to understand the vector addition, so let's say we have two vectors. One is the same, our x vector. We have taken another vector y, 1, 4. So if we just want to add these two guys over here, x and y, what we basically do, we basically add the x-axis details over here, like 3 plus 1, and the y direction details over here, 2 plus 4, the steps over here. So we get this 4, 6. So let us see it geometrically, how it looks like. So if I just see it in our Cartesian coordinate, so these are the 3 points over here, right? So this point is nothing but our vector x over here, because if I just measure this particular distance, so from 0 we went 3 steps over here, correct? And if I just measure this distance, from 3 we went up 2 steps over here. So that is my x vector, which is fair enough. Similarly, so this is my y vector, because from x direction, from 0, if I just go to one direction over here, like one step over here, we reach over here. Then from here, so if I just go up 4 steps, so I'll reach this point. So that is my y vector over here. Now as I said, when I add these two guys, I will add corresponding x and y direction values over here. So I'll get this guy over here, which is nothing but this point over here. So that means x direction, or basically right direction, whatever we see it over here from origin. So I'll go to 4 steps over here, correct? And from 4 I will go 6 steps up over here. So that basically when these two lines coincide, so that's my point. So this is my x plus y vector. Now if I just assume that like I do not have any kind of Cartesian coordinate system, so this is my x vector, this is my y vector, and this is x plus y vector. Now how I will know like how far I need to go over here, because I will not always write, if let's say if it is like 100 dimension vector, I need to write a very big one over here, big vector over here, then add corresponding elements over there and to determine like which point it will be. Instead of that, can we analytically see how it will be looking like when we are trying to add two vectors over here? Now if we see very carefully, this particular distance, this is one distance, right? And from 3 to 4 also 1. So that means I can bring this guy over here, okay? And this particular distance from 1 to 4, it's nothing but, if basically from 0 to 4, it's nothing but the distance 4. And if I just see it over here from 2 to 6, this is also 4 over here. So I can bring this guy over here, correct? Now if you see, if you are starting from this point, if we go right side 1 and up 4, I will reach this point. That means basically we are trying to generate the vector y over here. We can bring this vector y over here, correct? Just like we did in the previous slide, where we can start from any point and just to maintain these values over here, correct? Now it makes more sense. If you see it, like now we can formulate it very easily. So let's say if I just want to add x and y, what I will do is first I will basically draw the vector x. Now then from the vector x head, if I just start the vector y, that means vector y tail and vector x head, if it is basically coinciding the same point, then draw the vector y, then just basically add the tail of the vector x and head of the vector y. So that will basically give me the vector x plus y over here, correct? So this is nothing but the parallelogram law of vector addition. And if you see it, like if I just want to add vector x with y, that means y plus x, what I'll do, I will basically bring this guy. So let's draw it. So if we just draw this vector x, because what you need to do, from vector y head we need to start the vector x tail over here. So I can draw something like this one. I'm just not drawing through freehand, that's why maybe this line is not coming a straight line, but you get the idea, right? So this is nothing but my vector x over here, correct? So that means, so again if you see it, then if I just join the tail of the vector y with the head of the vector x, I'll again get this blue line over here, correct? So that means this blue line also represent vector y plus vector x as well, correct? So that means x plus y equals to y plus x as well. So this is nothing but a vector parallelogram law over here, so which we got it. So that means we got an idea about how vector addition works, and as I said, the same principle works for the higher dimensional vectors as well. Now let's see how the vector subtraction works. Okay, so for that we need to understand one simple logic. Let's say I have a vector called x, which is nothing but this 3.2 over here. Now if I just wanted to determine what will be my vector minus x, so we just need to basically multiply this one with the minus 1. That means both of these elements will be minus 3 and minus 2 over here, correct? So one interesting thing will be happening is the vector length will be same, but the direction will be changing to the opposite direction. That is what the concept behind the minus x over here. Okay, so similarly, if we have a vector called y, which is 1 4, so what will be my minus y? It will be minus 1 minus 4. Only thing is that I need to keep the same length, but my direction will be changing in the opposite direction. Okay, this will be my minus y. So now it's become very easy. So let's say if I just want to subtract y from x, so I can rewrite this stuff as x plus minus y. Okay, and that means x is 3 2 and minus y is nothing but minus 1 minus 4. So I'll get this guy over here, and geometrically if I wanted to see it, so this is my x, I have taken the same vector over here, and I need to addition, basically make a addition of minus y. So what I need to do, I need to take this minus y, and from head of x I need to basically draw the minus y vector over here, and then just simply join the tail of the x with head of the y over here to get the x minus y vector over here. Okay, the same principle works for the higher dimensional vectors as well. So now we know from our cost function how to get the yx minus a, correct? The actual output from the neural network minus the current output a from the neural network over here. Okay, and as I said, the same concept works for high dimensional vectors as well. And if I just wanted to take the length of this particular vector, what I will be doing is basically the similar concept. I will be basically applying that Pythagoras theorem over there to get the length of the vector over here. And how I will be expressing it the similar way with this double bar over here. Okay, so if I just want to visualize it in a 3D vector, because beyond 3D it will be very much difficult to visualize any vector geometrically. So let's say like I have three axes, x axis, y axis and z axis. Z axis is basically coming out of this particular plane over here. You can think of something like this one. So if you have a vector something like this one, so what will be its elements? For x axis it will be plus 5, then 8, then 3 over here. Okay, so this will be a vector, kind of it is coming out of this particular plane over here. We can visualize it in that way. Okay, so let's go back to our same slide which have started with, we started with this particular cost function. We understood why this yx minus a is needed, because we want to basically sum all of this, basically for all of the images we want to get the actual output minus the current output. And we know why this particular double bar is needed, because as we are dealing with vectors, so we need to basically take the difference of those two vectors and get that particular length over here. Okay, we also understood why we are taking squares, because of the same reason where we have talked about in the GRE example, otherwise it may cancel out each other, correct? And then we talked about why you are taking sum, because we want to basically analyze all through, basically we want to perform this stuff for all the images we are using for the training purpose, correct? And then we have this particular stuff, basically when we have taken this whole sum, we want to take an average as well. That's why you are basically dividing by n, which is nothing but our training number of training inputs over here. And if you see over here, there is 1/2 over here, because this is a quadratic cost function. And when we want to maximize or minimize, because our end goal will be to optimize it over here, and any kind of optimization problem we will be using calculus over here, correct? And this is where it lies, because if you see, we started with a very simple question, like why we have not used that particular cost function where we want to maximize the number of images correctly classified, because that will not be a smooth function of these weights and biases. So we will not know if I just change these weights and biases how that output will be changing, because of the same nature, because it's not a smooth function, because we will be using the calculus, specifically derivatives, to understand the behavior of this particular function. And to optimize it, we need a smooth function over there of weights and biases, basically of the inputs over here. And if you remember, in the machine learning video we also did the similar stuff. We have also taken the derivative over there, but in this case we have to deal with the vectors over here, a function which is basically taking vectors as an input over here. We'll see like how it goes over there, but at least we are able to understand why we are using a cost function, basically a quadratic cost function for the optimization over here. And can you use any other cost function instead of this quadratic cost? I think yes. We will see in the future like how to use other cost function as well. So this is kind of if when we move to the programming part of it, we will see like there are a lot of cost functions are available. We can basically try with different cost functions over there, but that is for the latter part of this one. Okay, so hopefully we got an idea about the cost function we have chosen over here, and different details about that one. From the next video onwards, we will start how to optimize this one, and we will learn whatever the fundamental stuff needed on the fly over there, as much as needed. Because if you see, like for the vectors, we have just touched base on the geometric representation and its addition and subtraction. There are a lot of other stuff as well regarding vectors, which at this point we may not need to know. If we want to explore more, I will give you a lot of good documentations as well, or links as well, which you can go through as well. Okay, so hopefully this video makes sense. See you in the next video.